Okay, so we're on page 5 of worksheet 2, quiz review. Okay, so number 1, find all critical numbers. So all we're doing here is finding the derivative and then setting the numerator and denominator of the derivative equal to 0. We may need to find common denominators, but we'll get to that when we deal with it. So first things first, I'm gonna get my expression ready for power rule. Okay, find our derivative. Do some cleanup. So we found our derivative, but we do see a denominator variable. So, that what we can do to get this to a point where we can find our critical values in a more straightforward way. Let's get it down to one fraction. That we can just focus on the numerator to find critical values as well as the denominator separately. So here I see 8 over x to 1/2. The 2x, I'm going to put a 1 underneath it so I can kind of see the need for common denominators since the denominators are different right now. Okay, so my common denominator is x to the 1/2. So here, bases are matching, so keep the numerator. Here, my denominator is not the same, so I need to multiply the top by x to the 1/2. So 2x times x to the 1/2. We're going to add exponents. 1 plus 1/2 is 3/2. So there we go. There's our ticket to getting our fractions to merge. So now to find critical values, critical numbers, I'll set the numerator equal to 0, denominator equal to 0, and whatever x's give me, those are my critical numbers. That's not going to come out to be a nice, pretty number. Cube root of 4 squared, you can leave it like that. That's fine. And square both sides, x equals 0. So here are my two critical numbers. Only ask for critical numbers. It's not EVT or first derivative test or mean value theorem or Rolle's theorem. You can stop there.
So when you get like with like when it's not distributed or it doesn't have a exponent that's like even.
Yeah, you can leave it alone. Yeah.
You multiply by the reciprocal.
Oh, yeah, that's right. That's right. Yeah. Anytime I want to move an exponent to the other side, I always just move basically multiply, raise both sides to the reciprocal. Because this will allow 3/2 and 2/3 will cancel out to be ones. That's what I want. I want x to the first power. Leave it like this here, or I can write it as cube root of 4 squared. Anything is fine. Okay, number 2. Find extrema. This is extreme value theorem. So we want to apply EVT. The only condition that's required for EVT is that our function is continuous. There's no differentiability condition for EVT because we can have sharp turns and it's okay because we're just trying to find the max. So we don't have to, it doesn't have to be a smooth curve, right? As long as the graph is continuous, all we care about is finding max and min. We're not trying to guarantee slope. So there's no need for differentiable. The only time we need it is if we're trying to guarantee a slope, but that's for rolls and mean value theorem. Okay, we got a polynomial. That's nice. Just have to state our conditions in our theorem. Looking for this on the quiz for you to make these statements. Hello. Page 5. Okay, so now that our function is continuous, the only thing that we care about with EVT is we do need to find critical values. And then we will see if our critical values are valid. If they are valid, then we will include critical values and endpoints, plug them all back into the original function, compare the y values, and look for the highest and lowest y values. That's what we care about, highest and lowest points. Derivative is easy, just go through power rule. Factor out of 3x. Okay, set equal to 0. Solve for x. Okay, so the next decision we have to make is, are both of these critical values valid? How do we decide whether we want to test these or not? Interval, yeah. So we look at the interval. We only care about the interval. So anything that's outside interval is not part of our problem. 0 looks to be safe. 0 is between -3 and 1. But -4 is outside the interval. It is critical value, but it's not part of our problem. So we're not going to include that. Okay. So we have to make sure we test 0 as well as endpoint. Sometimes students just rely on their critical value, which is a candidate for sure, but we don't want to forget about the fact that we're always having to involve endpoints as well. So here we have 3 values we need to test, and they all go back into the original function to find the max and mins. Okay, use your calculator. -27 plus 54. So then all we care about are just looking at these numbers here, and we're just comparing these numbers to find the max and min. Oh, sorry, 7. Thanks. highest y value is 27, 0 is the lowest y value. All I care about is the y values. So you just say absolute max is 27. Absolute min is 0. Page 5. Okay, so number 3, Rolle's theorem. So Rolle's theorem, remember the goal of Rolle's theorem is to see if we can guarantee a slope 0, and if once we can guarantee that there's a slope 0 somewhere on the curve, we're going to look for the location where that slope 0 is going to exist. So with the Rolle's theorem, the big idea is that we want to guarantee a slope 0. So to guarantee a slope, we have to confirm that our graph is not only continuous, it needs to be differentiable as well. It needs to be a smooth curve. But the nice thing is this is a polynomial. There's no denominator to worry about. Our function is continuous and differentiable, guaranteed for the entirety of the domain, but we want to specify the interval. Okay, brackets for continuity, parentheses for differentiability. There's one more thing we have to confirm is that our endpoints have to live on the same y value, because we want to guarantee that our endpoints are across from each other so that we can draw a horizontal line between it so that we can guarantee a slope 0. So one more thing we have to confirm. Look at the endpoints, back to the original function, no derivative yet. Two squared minus 16 plus 5. Yeah, negative 7, right? Okay, so we know that they are directly across from each other. They have the same order pairs, which means that the slope between these 2 points must be what? 0. Okay. I see some students, they do this, they say, oh, these are the same numbers, so I'm going to set slope equal to -7. We don't want to do that, right? The fact that we're talking about slope and not the fact that they do share the same order pair, but it's just the fact that it's a slope 0, that's what's important. Okay, we're going to find our derivative and set our derivative equal to 0, and we're going to look for a location on the curve using the derivative to help us find that location where slope 0 occurs. Okay, so f prime. Okay, let's make sure we understand where that 0 goes. That 0 is going to go in for the slope slot and not for the x slot, right? That's mismatch, right? We want that 0 to be here. So we're going to ask the curve to ask the derivative to tell us, okay, where on the curve is there a slope 0? Because I know there's a slope 0 between 2 and 6. We've guaranteed it. I'm going to look for that location. Divide both sides by 8, x equals 4. And just to confirm, our location should always live between the endpoints. If it doesn't, something went wrong, because it's a guarantee. We should be able to find at least one location that lives between our interval.
Or C sort.
Yeah, so they're asking for the C value here, so it's just another way of saying their way of saying their X value for this theorem. Okay, number 4, mean value theorem, same idea, but we're still going to go through the same process, continuity, differentiability, look for the endpoints, look for the Y values, but now it's not as restrictive. These, for mean value theorem, the endpoints don't have to be directly across from each other. It could be any value, and the slope doesn't have to be 0. It could be slope 0, but it could be slope 3 or 4 or -8, 1/2. But we have to look for that slope. Okay, so same process, right? It's just that this has to be slope 0. The mean value theorem can be any slope. But it's the exact same process. Okay, again, nice polynomial here.
So yeah, if it was a fraction.
Yeah. Right. We would look for a vertical asymptote by setting the denominator equal to 0, and then seeing if the location of that vertical asymptote disrupts the interval. If it disrupts the interval, then we have an issue. Our function is not continuous. But if it doesn't disrupt the interval, we're safe. We can state the conditions and continue moving forward.
So you just look in the denominator.
Just look at the denominator.
So if it was continuous, is it always different?
Yeah, the ones I give you, if it's continuous, it'll be different. We do have some exceptions, but we can talk about that later. There are very few. Okay, endpoints, just like how we did with mean value theorem. Make sure that you don't touch the derivative just yet. You just want to gather information. Sorry, I said G of X, but I'll say F here, just like right as. Okay, find slope. Change in Y over change in X. Yeah. Now we can find the derivative. Power rule, 3x squared minus 1. So now we're going to basically ask the derivative. We know there's a slope 6. Can you tell us where that slope 6 is going to live? So hit that 6, put it into that slope slot. Solve for X. Take the square root of both sides. Don't forget there's a plus or minus that shows up when we take the square root of both sides. So we get X equals root 7/3 and negative root 7/3.
Okay, is there a decision we have to make at this point? That's right, see which one is inside the interval. We're guaranteed at least one, but if there's more than one, I usually consider that as a red flag because it's possible that both of them are inside interval, but there's a chance that one is inside, one's outside. In this case, we do have one that's outside the interval. √7/3, you plug that in the calculator, that should be nice and safe between 1 and 2. But negative √7/3, that's definitely in the outside our interval. So we can remove that. That's not a location. It is a location where there's a slope of 6, but if it's not part of the interval, it's not part of our problem.
You know how to do the number line?
No, because all we care about is the slope. We're trying to guarantee the slope. It's not first derivative test, it's not concavity test, so there's no slope sign. All we care about is there a place where there's a slope 6? There is. Let's just find that location. That's all we care about. Okay, page 6. Okay, interval where function is increasing, decreasing, relative max, relative min. So now we'll go through this is the first derivative test. We'll find f prime. We'll set the numerator and denominator equal to 0. We'll take all the critical values, put them onto our number line, passage interval, and make our statements. Okay, so for this problem here, I got to go through quotient rule, f prime g minus f g prime all over g squared.
Clean this up, distribute through.
Okay, we set the numerator equal to 0, denominator equal to 0. Those are where we find our critical values. Okay, we take our 3 critical values, place them onto our slope sign line. Test against our derivative. Find some test points. To the derivative, negative 18 times negative 4, that's positive. The denominator I'm going to ignore because it's squared, so that's nice because we know the denominator is always positive no matter what we do with it. So once we find the sign of the numerator, we have the sign of the whole fraction. So negative 18 times negative 4 is positive. Positive over positive. Insert -1. -1 times -18, that's positive over a positive. Plug 1 into the derivative, 1 times -18, that's negative, over positive is negative. Plug 4 in, 4 times -18, negative over a positive is negative. Okay, after this, we don't care about these test points anymore. Make sure you don't include them in any of your interval statements. But now we can clearly see where the increase and decreases are. Make sure that you don't try to merge these together. Okay, there's actually vertical asymptotes at 3 and -3. So I think the safest thing to do is don't try to merge any intervals, even though it looks like they could. Just always keep them separated. Okay, so we have interval increasing in 2 separate intervals, interval decreasing in 2 separate intervals, and what do you expect at 0? Okay, what do you say? What do we call that? A relative max, yeah. So it's asking for relative max points. So you can plug 0 back into the original function to get the order pair, and then you have all your because statements you have to write out as well. Make sure you're spending time and writing out these because statements. Okay, number 6. Find intervals where graph is concave up and concave down. Find points of inflection. Same process as number 5. You just have to make your way down to the second derivative. But then once you make your way down to the second derivative, you set the numerator and denominator. If there's a denominator equal to 0, create your second derivative sine line, test your intervals. But now your intervals will but from the second derivative, your intervals will tell you information about concavity and points of inflection instead of max and min. So make your way down to the second derivative function, f prime, power rule, f double prime, also power rule. Okay, so f prime, go through power rule, I can get it all the way down to 2x cubed plus 6x squared. Second derivative, go through power rule again, 6x squared plus 12x. Set that equal to 0. Solve for x, you get 0, -2. So now -2 and 0 will go onto your second derivative sign line. Okay, choose values in each subinterval to test. Here I can test -3, -1, 1. They each go into the second derivative factored form. -3 goes in for x, that's negative times a negative is a positive. So for the first interval, I'm going to put a u to indicate my graph is concave up. Insert -1. 6 times -1, that's negative. -1 plus 2 is positive. Negative times positive is positive. Sorry, negative times positive is negative. So second interval is negative, concave down. Third interval here, 1 in for x, positive times positive, concave up. So I can make my statements about where my graph is concave up, where my graph is concave down, and how many points of inflections do you see? 2, because there are 2. Both these critical points are candidates, and they pass the test because there's a change in concavity curvature on both sides of my critical point. And I'm looking for points, so I'm going to find the y values. So how do I find the y values of these into the main one, original? Yeah. Then, of course, focus on your because statements as well. Oh, I put f -2, but I meant to plug it into the original function and actually get those y values. -2, -8, and 0, 0. Okay, any questions? Okay, number 7, use the second derivative test to find relative extrema. Okay, so second derivative test does the same thing as the first derivative test. It finds the max and mins, but it just goes through a different process. Rather than creating a sign line, we're going to plug the critical points from first derivative into the second derivative function. Okay, but we're going to start off the same way. We're still going to find f prime. We're still going to set f prime equal to 0. We're still going to set find our critical points from f prime. But from there, our paths will differ between first and second derivative test. With the power rule. Okay, we still set f prime equal to 0. I like to factor with my first term being positive. multiplies to be a times c, which is 45. Adds up to be negative 14. I have 33. So what about negative 5 and negative 9? Negative 9 times negative 3, negative 5 is 45, negative 9 plus negative 5 is negative 14. Reduce if I can. Solve for x. X equals 3 and x equals 5/3. Now we know that these are our candidates, but rather than doing a slope sine line, right, we're going to do something else because that's the first derivative test. We're going to determine whether these are max and mins going through a different method, and that's the second derivative test. Okay, so we're going to find the second derivative function. So we go to our f prime, make our way down to the second derivative. I get negative 6x plus 14. And now I'm not going to set this equal to 0 because that's something else. I'm going to insert the 3 and 5/3 into the second derivative. And based off of the value that I get, I'm going to make my conclusion whether these points are max or min. So I get negative 18 plus 14, which is negative 4. So how does that number help me out? The number is not that important. It's the fact that it's what? Negative. So we have to verbalize this here. A negative second derivative means what? Concave down. And we already know these are places where slope is 0. So if I pair slope 0 with concave down, the only conclusion that I can make is that this point at 3 must be a what? Relative max. So we're not going through this process now. If we went through first derivative test, we'll be able to confirm that indeed it is a relative max, but that's a different method. We're going through this method here. Same idea. We'll enter 5/3 into the second derivative function. So negative 6 and 3 reduces to be 2. Negative 2 times 5 is negative 10. Negative 10 plus 14 is 4. So positive 4. The number is not that important. It's the fact that it's positive. So let's verbalize this. Positive second derivative value means concave up. And if you can graph a concave up graph, the only point that's staring back at you in terms of a relative max, relative min is a relative minimum. Okay, number 8 is just a matter of using all these notations to work backwards to create a slope and concavity sine line, and then trying to sketch your graph to match that. So we'll try to do this in class, and I'll do another help session tomorrow morning. Thank you.